This video covers charge density and flux. Up until now, we've only talked about electric fields coming from point charges, but we can also talk about charged plates which create electric fields in between them. Now, this electric field will always flow from a positive charged plate to the negative charged plate. Now, if we orient the charged plates the way we see them here, then the electric field goes from top to bottom, similar to the gravitational field, which goes from also top to bottom. Now, here you see a point charge being placed in this electric field, and we know that these point charges are going to be repelled by the positive side and attracted to the negative side. Same thing, if you have a mass and you place it in the gravitational field, it's going to accelerate towards the ground. This analogy between electric fields and gravitational fields is only used to help you understand the similarities in between the two. Now, we know that masses will never go upwards unless there is a force applied, which gives it some inertia to go upwards. But in electric fields, if we place a negative charge in that electric field, then it will actually go away from the negative charged plate towards the positively charged plate. So that's our biggest difference here. Now, one of the important experiments you're going to need to know is the Millikan's oil drop experiment. What Millikan did is suspend a charged oil drop between two charged plates, as shown in the diagram here. So in this experiment, in order for him to suspend this oil drop, the electric force upward had to be equal to the gravitational force. Now, if he knew the strength of the electric field, he could determine the charge on this oil drop. Now, he did several trials, and he consisted of charge values shown here. Now, all these values are multiples of 1.6 times 10 to the negative 19. And we know from the beginning that that is the charge for an elementary particle, meaning the charge on one electron or one proton. So with Millikan's experiment, he was able to determine the elementary charge on an electron. Now, electric field density is going to be the focus for the rest of the video. When we draw electric field lines, the strength of the electric field is evident by the closeness of the lines. We went over this last time. So where we see the lines that are close together, that means the field is strongest at those points. If the lines are parallel, then that means the field is uniform, like in between two charged plates. A strong electric field will have more electric field lines passing through an area of space, and that's the part we're going to look at today. In order to standardize electric field comparisons, we need to use the same area every time we test an electric field strength. And the SI unit for area is square meters. So let's look at this example. It says, where is the field the strongest in these scenarios? Well, again, when our electric field lines are closest together, that means that the electric field is the strongest. As they get further and further apart, then our electric field starts getting weaker. So in this example, area 3 shows our highest or strongest electric field. In this example, we're asked to solve for where the electric field is strongest. Well, because the same amount of electric field lines go through the same area, then the electric field is the same in all four areas. So conceptually, you can think of the electric field density as the number of field lines passing through an area of space. Now, the line density, or the lines per area, is proportional to the electric field strength. Again, the stronger the field, the more lines in the same area. So if we multiply the electric field E by the area A, it gives us E times A. E is not the number of lines, but it's proportional to line density. Basically, it gives us an idea of how much electric field is flowing through that area. This is going to be known as flux. So electric flux is the flow of the electric field through a square meter. Okay. The variable for electric flux is going to be this symbol phi with a capital E at the end to show electric flux. We're also going to have magnetic flux. In this particular section, it's not going to be entirely important to label it with an E every time. But it is a dot product, which means that these two components, both electric field and area, need to be parallel to each other, like we saw in the work equations. Now, you might say that area is not a vector. Well, that's true. But in physics, we can describe a normal to the surface as a vector. When we say normal, remember that means perpendicular. So we're looking at a vector that's perpendicular to the surface of our area. This will be a vector. And we want this normal vector to be parallel to our electric field. Again, the units for electric flux are Newton meter squared per coulomb. So remember that the electric field is Newton per coulomb and area is simply meter squared. Remember that when you see a dot product, think parallel components. So you need to find the component of the electric field or the area vector, the normal vector, that are parallel to each other. Now the equation is EA cosine theta. Again, that theta is going to help get the components parallel to each other. Now this angle is the angle between the electric field and the area normal vector. So that angle needs to be measured from the normal, the line perpendicular to your surface. In this example, we're asked to determine the flux when a 20 Newton per coulomb electric field passes straight through an area that is 10 centimeters by 10 centimeters. So we need to first convert these centimeters to meters, and then use that information to help us find the area of the square. Now, the electric field is going right through this square. If you notice, the line that is perpendicular to our surface is already parallel to our electric field. So the angle between them would be 0. So in this case, you can either drop the cosine entirely or put cosine of 0. So 20 is our electric field, a 0.10 by 0.10 is our area, and we get 0.2 Newton meter squared per coulomb. In this example, you're asked to determine the flux when a 20 Newton per coulomb electric field moves past an area that is 10 centimeters by 10 centimeters. Again, this doesn't tell you the direction that the area is oriented in this electric field, but you are given a picture in this case. Now, the normal vector is going straight up, and our electric field is going to the right. So we can see here that the angle in between our normal vector and our electric field is 90 degrees. So the cosine of 90 is 0, meaning that the flux that goes through this area is also 0. In this example, we have the same electric field going through the same surface, but now the field strikes the area at an angle of 60 degrees as measured from the surface. So this angle that we're being given is 60 degrees from the surface, which is this theta right here. But remember that the angle between the electric field, which is here, and my normal vector, which is here, gives us an angle of 30 degrees. Again, another way to look at that is if my electric field is already going in this direction and my area vector is going off in this direction, then the angle or the component of the electric field that also goes parallel to my area would be the electric field times the cosine of this theta, which in our case is 30. So plugging in all of our information, we get 0.17 Newton meter squared per coulomb. Now this sign convention for flux is going to be more important for the next section, but it's important to get a grip of what it means right now. Now, flux that goes into an object is going to be considered negative, and flux that comes out of an object is going to be considered positive. Again, if you want to use our gravitational field reference, lines pointing toward the center of Earth, into or down, are negative, and lines pointing away from the center of the Earth, out of or up, are considered positive. So that will help you remember this information. Now, here we have two charge plates. From the direction of the electric field lines, we can tell that this red charged plate is positive because our electric field lines go away from it. And this blue line, or this blue plate, is negative because our electric field goes towards it. Now, here we have a common closed surface, a sphere. Now, if you look at the amount of electric field lines that are going in on the left-hand side is the same amount as the electric field lines that come out on the right-hand side. So a common question for this type of problem is, what is the net overall or total flux through the sphere? Well, for every negative field line, it has a corresponding positive field line, meaning that the net flux is 0. That's actually true whether or not the field is uniform. So in this example, we're looking at a charged particle. Here, because of the direction of the electric field lines, I can tell that this is a positive charged particle. And we are placing this sphere some distance away from my point charge. Now, if you look at the left-hand side, the electric field lines are closer together, but the area is smaller. On the right-hand side, the electric field lines are further apart, indicating that they are less, it is not as strong on the right-hand side, but the area is much greater. So even for this example, the net overall or total flux through the sphere is still going to be 0. Because the negative large field passing through the small area will be canceled out by the positive small field passing through a large area. Remember that as it goes into, it's considered negative. As it comes out, it's considered positive. So again, our net flux through the entire closed surface is still 0. Even if our object takes another shape, in this case, my area is not easily to determine, and our electric field strength also changes on the left and the right hand side. But my flux is still overall 0. So that means that the net flux through a closed surface is 0 whenever the excess charges are found outside the closed surface. That's what this picture is showing, a charge outside of a closed surface. So let's say that you're asked to solve for the electric flux through a curved surface. Well, when the electric flux field strikes a curved surface, the angle between the field and the normal is a problem. Each of the 3 vectors shown here has a different angle measured with respect to a normal. But we can divide up the area into smaller, more manageable segments. Then we can split up the electric field into smaller vectors, one for each area. Now, if the areas are divided and the electric fields are divided by the same amount, the ratio from area to electric field still remains the same. So we haven't exactly changed anything. Now, what we can do is shrink the areas enough and they will be nearly flat. When this is done, then you can solve for all of these fluxes and add them together. When you add up the infinitely many little fluxes, then you can rewrite our equation with this shown here in the red box. Now, this is going to be the focus of our next couple of lessons, but it's important to introduce it now.